And transcellular fluid is measured in a different way, not like how the other fluid compartments are measured. So we'll be discussing about how to measure these fluid compartments now. So how to measure. So how do we measure these fluid compartments? How do we know that the ECF is of 28 liters and the is of 14 liters and the ICF is 28 liters, and that we have 75% of the ECF in the interstitial, mesenchymal, and transcellular compartment, and 1/4 of the ECF in plasma? So this is because we do something called the indicator dilution method. Indicator dilution method. And what is this indicator dilution method? So this is a method that helps us to measure the different volumes of body fluid compartments based on the and it's based on the law of conservation of mass. So law of conservation of mass. So what is happening over here? Well, as the name indicates, indicator. Indicator means it's something that we can measure, which indicates that this substance is there, okay? So there's a certain substance which you don't find in a particular compartment of the body, which if I inject in that part of the body, it should stay there, and that should easily be measured later after some time. And dilution. So what happens is, I want to measure a certain amount of fluid that is present in a vessel, as an example over here. So there's this vessel that you could see over here, and there's some water in it, and I don't know how much water is in it. So this is water, a plain water over here, and now I have a small container over here. I'm going to draw it in the form of a little syringe so we can relate to it even better. So there's this little syringe, and we have a needle over here, and we can measure the amount of volume over here. Now this is a big bucket of water, and that syringe is relatively small, comparatively small, with reference to the bucket. So now let's just imagine that we have a very small amount of fluid in this syringe. Let's say it's 1 ml of fluid, and we have an indicator, a substance, some chemical. Let's call it chemical X. So chemical X, okay, it's some special indicator substance over there, and let's say that it is 1 gram of chemical X that is present in this syringe over here, in this syringe. Now, so that means that the concentration of chemical X in this syringe is, concentration is mass per unit volume, so that is equal to 1 gram per 1 ml. So that is 1 gram per ml of chemical X. This is the concentration over here. So this is in the syringe and in the bucket. So let's call this syringe compartment B, and the bucket is compartment A. Okay, now I know the volume in compartment B, which is the syringe. It's, you have the gradations over here. I know the concentration, I know the mass of the substance. Now this chemical X does not exist in this compartment A naturally. It's not over here. Okay, I know that because I can measure. I can take a little sample of this fluid and I can measure it, and there's no chemical X in it. Now I'm going to inject or transfer this content of compartment B into compartment A over here. I'm going to inject it into this compartment. Now what's going to happen is, you could see that this is a lot of fluid in the bucket compared to that little syringe over there. So what's going to happen now? The chemical X is going to get even more diluted. So there's going to be much lesser concentration of chemical X in compartment A than we had in compartment B. So there is a difference in the concentration over here. So the concentration in compartment A is going to be, again, mass per unit volume. Now the mass is the same. It's 1 gram in the syringe, and when I inject it, it's 1 gram in the bucket. So the mass is the same. I know the mass is the same on both sides, but the volume of compartment A is different from the syringe, which I'm going to call compartment B. So what happens is, if the mass is the same but the concentration and volume changes, and in this case this mass I'm going to call is the same 1 gram, and the compartment B has a concentration B and volume B. Can I cross multiply and find out what is the volume that is unknown? In this case it's volume A. I don't know what this is. Remember, I don't know the volume of the bucket, but I know the syringe's volume over here. So what I can do is I can rearrange this as CA VA equals to M, which is equal to CB VB. You see what I did over here? It's the same mass here and here. And CA VA is equal to CB VB, which is equal to M. So that means now I know that there is a certain volume of VA which I can't be aware, which I'm not aware of right now. But when I cross multiply this and bring the CA down here, now what am I going to do? I'm going to get the volume of A over here, so of compartment A. And this is the principle of the indicator dilution method. I can find out the change in the concentration of a certain substance, an indicator substance, when I insert it into a certain compartment of fluid. It changes its concentration, and because I know the mass that has already been injected, I can predict the volume and I can calculate the volume. However, so you need particular indicators, and these indicators have certain qualities that you should be aware of. So a good indicator is supposed to be, and the properties of good indicator are, first of all, if you want to inject it, you want to make sure that it is non-toxic. Number one, it's not toxic to the person, because you are still going to inject this in a living person. Non-toxic. So you're going to inject this indicator into a person, and then it's going to just go to the particular compartment that you want it to go into. So it should go where you want it to go to. So it should go to the compartment that it is meant to go to, that it should go in, and it should not go to other compartments. It should not go to other compartments, or you'll get an even further dilution and not an accurate representation of the concentration change, and hence the math is all off. And then if you look at it, it should not be eliminated by the body, eliminated or metabolized by the body. No, sorry, let's just by the body. Let's just drop that. Or if it is metabolized, or eliminated or excreted, it should be easy to compensate for in the equation. So it should be predicted and compensated for by the math equation. So this is a very important thing, and of course it should be easily measured. So this is the feature of your good indicator that you would be using over here, right? And so we have different indicators for various body fluid compartments, and I want you to be aware that you cannot measure every single fluid compartment. So let me just elaborate. So you have different fluid compartments like ICF, ECF, and all of that. However, where are you going to inject the fluid? So you're going to inject it usually in a vein or in a blood vessel. That is part of your plasma, which is part of the ECF. All right, and after some time, after the indicator has distributed evenly, that's another important thing. The indicator should distribute evenly in the compartment to be measured, you are going to collect some fluid again. Now, which fluid are you going to collect again? It's going to be plasma again. So this indicator is going to be used to calculate the volume of any fluid compartment which is actually continuous or which includes your plasma, and so you should be aware of this. What does that mean? That means I can calculate with the indicator dilution method my plasma volume, my ECF volume, or my total body water. But when it comes to interstitial fluid compartment or intracellular, I can't do that. So what do? If I can calculate plasma, ECF, and total body water with various indicators, but I cannot calculate interstitial and intracellular fluid with indicators. Just remember this, all right? Because the fluid goes through the plasma and then to the other compartments, and the quantity and the should be the same. The concentration should be the same with the plasma over there. So that means that if some compartment is not continuous over there with plasma, if is not in contact with plasma, you're not going to be able to take that fluid from that compartment so easily. You'll only be able to extract plasma back again. So for that reason, we can only estimate with indicators plasma volume. You can even measure red blood cell volume, you can measure your ECF volume, and you can measure total body water. But when it comes to ICF and interstitial fluid, you will have to actually subtract one value from another. Like if you want to measure interstitial fluid compartment, I can measure plasma volume and I can measure extracellular fluid volume, and then I can subtract them from each other, and then I can get your interstitial fluid compartment. So that's how it works over here. If I want to measure intracellular fluid compartment, I can measure your ECF using indicator dilution method, then I can measure total body water using indicator dilution method, then subtract it, and I get ICF that time, intracellular fluid compartment. So the list of indicators that exist are first of all, we have indicators for plasma. So the indicators used for plasma is Evans blue, also known as T1824. T1824. We also have albumin that's tagged with an isotope of iodine, a radioactive isotope of iodine. So albumin is a large molecule, and it's got this one iodine tagged to it, and this iodine is it's different from the albumin which is in our body. So it can easily be measured by using special equipments in the lab over there. So iodine 125 albumin is one of the most commonly used indicators for plasma volume. If we want to measure RBC volume, what can I use as an indicator? Well, I'd take other RBCs and I would tag the RBCs with radioactive chromium, or like isotopes of chromium, 51 Cr or 59 iron, which is already present in red cells, and even 32 phosphorus. So if I do this, or even with certain antigens, so I can inject a few red cells into your blood, but these red cells are a little different, and then as they mix with your blood, I take a little blood sample and I get your red cell volume over there, and that is going to be easily calculated from this. So antigenic tagging is one more thing. Tag RBCs. So the machine can later take the diluted sample and see the change in concentration that exists. Same thing with total blood volume. What I can do for this is I can calculate total blood volume equals to plasma volume divided by 1 minus hematocrit. Now how is this? This is mathematics. It's easy. We know hematocrit is around 40% or 45%, so that comes to 0.4 in some people, or 0.45 in males usually if they don't have anemia. So if we just do plasma volume divided by 0.6 in males, that would give me my total blood volume. So using some mathematics we can also calculate. ECF requires a substance to be injected which is going to stay in the ECF. So inulin, not insulin, inulin. This is a polymer of sugars. It's around 5,000 atomic mass units, and this is one of the most accurate indicators for inulin. We actually extract this from the Jerusalem artichoke. So this is one of those very delicious vegetables that you could enjoy actually, and it is made of it's got a lot of carbohydrates and fiber in it, and it tastes very good when it's deep fried. Anyway, so inulin is one of those substances which we use, which we can inject, and which we get from the Jerusalem artichoke. Then we have something called sucrose. Sucrose is just common table sugar we use, okay? And then we have mannitol. This is again a polymer of sugars, of carbohydrates. Then you have other substances like sodium thiosulfate, sodium thiosulfate. And then you have sodium thiocyanate, or even isotopes of sodium with an atomic mass of 22. Iodine 125 labeled iothalamate. So these are all the indicators for ECF. Interstitial fluid, I told you, we can't measure it with indicator dilution method so easily. So for interstitial fluid, we take the ECF volume by using the above mentioned indicators minus the plasma, and then we have intracellular fluid. Again, we can't measure this with our normal indicators. So what we do is we take total body water, and then we subtract it from the ECF, which we again calculate with the indicator dilution method. For total body water, I have to give an indicator that goes to all the compartments equally, just like any other water molecule. So I would sometimes ask my students as a joke, what is water but different from water? So when we think of water, we would usually think of H2O, right? And that's the normal hydrogen with an atomic mass and atomic number of 1. What if we used heavy water instead? D2O or T2O. So tritium oxide, this is the heavy water that they use for even in these nuclear power plants and all of that, where the hydrogen has an atomic mass of 2. So that's technically water but not water. So it can easily equally distribute to all of the other compartments in the body. And also the other thing is antipyrine.